traversable graphs, Eulerian and Semi-Eulerian graphs. A traversable graph has a trail that involves every edge. Can't spell today. So the definition of a traversable graph, it's got a trail that involves every edge, and so the Königsberg bridge problem is one of these, remembering that a trail has the definition of no repeated edges. So you have to, for a graph to be traversable, it has to be, this is a particular definition. The graph is traversable if it has a trail that has every edge and no repeated edges, exactly like the Königsberg bridge problem. And what we need to be able to do is check if graphs are traversable. Now you can just do it by inspection. So a cycle is fine, because remember, a cycle is a closed trail. So here, 1, 2, 3, 4, I did every edge and every edge only once. So you can just check. But sometimes when you get to more complicated graphs, you do want a rule. So a graph must be connected, because otherwise, of course, we've got a slight problem. Must be connected. And because Euler came up with, a lot of graph theory, if we can traverse a graph, we can describe it as Eulerian or Semi-Eulerian. We'll talk about the definitions of that after a quick example. Now, you can check if a graph is traversable. You might remember what Euler came up with. If all vertices have even degree, or we have two vertices that are odd and all the others are even. So a graph, a traversable graph, will have either a trail, a circuit, or a cycle that uses every edge in the graph. So we can quickly check the degrees here. Those are all 2, they're all even, therefore it's traversable. And we could quickly show, where's a nice coloured pen? Yep, it's traversable. If we check all degrees here, 3, 3, 2. Okay, at most 2 vertices can be odd. So here we will be able to traverse the graph, but only if we start and end at the 2 odd ones. So see, it's okay if you go back to vertices more than once, but you cannot go over any edge more than once. Two, three, 3. Oh, not traversable. Because more than 2 vertices are odd. Now, Eulerian graphs are graphs like this first one, where we have a circuit, a closed trail that includes every edge. So you remember a circuit starts and ends at the same vertex. So they have a circuit that includes every edge, and you'll see that for the graph to be able to be closed with a circuit starting and ending here, for example, we can't have any odd vertices. So an Eulerian graph must be connected and have all vertices of even degree. So an Eulerian graph can start at any vertex, I could have started that anywhere, and finish at the same vertex. A semi-Eulerian graph has an open trail. Oh, have. Sorry, I was in the plural there. Sorry, my writing got messy there. Has an open trail that includes every edge only once. I probably should have said only once up here. And so these must, so an Eulerian trail and an Eulerian circuit include every edge only once. A graph that has an Eulerian circuit is an Eulerian graph. A graph that has an Eulerian trail is semi-Eulerian. So it must still be connected and have exactly two odd vertices. And our trail will start at one of the odd vertices and end at the other odd vertex. Now, it's hard for people sometimes, we're going to learn, sorry about the bell, we're going to learn about Hamiltonian graphs and paths and cycles. Eulerian starts with an E and is all about the edges. So this is the sort of problem where you're trying to travel each road only once or something like that. Next up, we'll look at Hamiltonian Hamiltonian paths and cycles, and they deal with going to every vertex.